It's on my phone for this one. So I won't go into too much detail about what the study was about, because of course you're about to hear that. But just to give a bit of background for those that don't know how this started, we ran an OSIP campaign to see what sort of ideas that we could get in about quantum information processing with some applicability to space. So it was a really large call, and we saw quite a lot to do with near-term quantum computers, a lot of annealing, these sorts of projects, but we didn't see much on things that you could implement straight away. And this project was something that we could work on right now with kind of fast rewards. The circuit compilation problem is something that will apply to very near-term quantum computers and will be a very essential step into getting some first use cases for noisy computers as well. So our main presenter today, I imagine, will be Angela. So if I could pass over to you. I don't think I have much more to add. Ooh. I can't hear anybody else.
Yeah, I think Angela's
is muted.
All right, Ashley, are you muted?
Yes.
Yeah, I can see your
microphone. Okay, so
okay.
Okay, we share the. Do you see the screen?
Yes.
Okay, so I will go to the summary, and next the details will have. So Ricardo will present together the details of the study. Okay, so you know the title. So this is the final presentation of our Ariadna study. Meta-heuristic algorithms for the quantum circuit compilation problem. Okay, so the outline of the presentation, of course, first of all, the executive summary, next the details of the study. Okay, just a few words about the conventional versus quantum circuit. A quantum computer is able to execute algorithms, and algorithms are represented with quantum circuits. A quantum circuit is a set of quantum gates which operates on Q bits. And basically, we have here an example. So there is analogous, so the quantum gate is an analogous of the gate logic gates, and qubits is the counterpart of the bits. And here we have an example of a quantum chip where there is 8 qubits, which is this chip is able, in principle, to execute the quantum gates, which represents the instruction of the algorithm. Okay, this is an intuition about the compilation problem we are going to solve. We start from a problem specification, for example, the max cut, which is a very famous problem in quantum computing. And we realize an ideal quantum circuit, so a sequence of gates, which basically implement the solving procedure for the max cut. And next, as a next step, we need to compile the circuit to a specific processor, specific quantum machine, for example, in IBM or Google or Rigetti or so on. And the problem is to insert in the ideal circuit, which is a set of gates, a particular gate called a swap gate. In this case, in this figure, the swap gate are the yellow blocks, and the other one are the original gates from the ideal quantum circuit. Okay, just the intuition about the gate, the problem. So suppose here we have a quantum processor with 8 qubits, and the edge of represent the physical gate where we can execute the quantum gates. Okay, and on the other side of the slide, we have our circuit, which is composed by mix, swap, and PS gate. Basically, executing the algorithm means to execute all the blocks in the circuit. For example, here we first of all we map on the circuit the state, the initial state of the circuit, and next we go to the execution. First we execute, for example, the gate between the state 4 and 6 here, and they are adjacent, so are allocated on a physical gate, so we can execute it. We noted that the next gate is on the 3 and 7. 3 and 7 in the initial state were not adjacent. Now you noted that the swap, no? The swap procedure. Okay, this is the effect of the yellow blocks, the swap. So we need to insert this swap in the circuit in order to make feasible the computation on the quantum processor. Okay, next we go to execute the gate. And so the 3-7 is now executed, and we need to swap other and so on. Okay, but just to have the intuition. Okay, so our study was about to infuse, in some sense, quantum computing in space. So the aim was to explore the use of quantum computing as an accelerator in the resolution of optimization problem in space. So the problem is our quantum algorithm better than a classical algorithm on a classical computer? Okay, this was in some sense the frame where we reason. And what we did exactly. So we studied the compilation, the problem of the compilation of quantum circuits for this kind of, for noise intermediate scale quantum devices, which are the device which needs swap. And for this device, we have used a particular method to implement optimization algorithm, the so-called quantum approximate optimization algorithm, which is our template, our way to implement, for example, max-cut or graph coloring problem, and so on. And next, the idea was to find one or more applications for space to use quantum computing. Okay, and what about the QoA? Now, the question is, but okay, we compile, but are we able to do better than a classical computer? Okay, this is just a slide to focalize on this problem, which is behind what we are doing. Because if we compile quantum algorithms, it's because we hope to be better than a classical computer. And now, just want to cite this paper. It's a recent paper from Heuristics and Matsuura, where they have studied exactly the QoI approach to implement optimization algorithms for the specific max-cut problem, which is one of the problems we can solve. We will see a circuit to solve the max-cut, for example, problem. And the conclusion was, okay, we will be able to be better than a classical computer when the number of qubits of a quantum computer will be around 1,000 of qubits. Here, on the right, you see for example, the IBM quantum roadmap. Now, if you know, there is a month ago, IBM proposed a 127 qubits processor. And according to their prevision, in 2 years, they will be able to to propose a machine with 1,000 more than 1,000 qubits. So we are at least for the max cut and with the QA approach, maybe we will be able to do better in a couple of years. But okay, this is just an estimation. Okay, now after this, just a few words about our study in general. So the idea in this study was to define heuristic algorithms for compiling circuits. Because why heuristic? Because we think to compile very large circuits. Because generally in computer science you use heuristic when you want to solve very difficult problem in size, and we think to solve very large problems with in order. So if for this motivation we propose heuristic algorithm. Next, the second goal was to find a relevant application for space using quantum computing, implement our ideas or proposal for example, in Python, and propose some empirical results. So, what about our contribution? We have proposed an algorithm for the max k-cut problem, which is a generalization of the well-known graph calling problem. And why graph calling? Because we know some scheduling problem, some can be reduced to the graph calling. In fact, what we propose here is an application which is the satellite scheduling problem, which can be reduced to max k-cut. And next, the other contribution was a Python module which used the QSkit framework, which is a well-known framework for for working on quantum computing. Okay, and just a few words about this is the algorithm, the schema of the algorithm, which is the compiled algorithm, which is greedy randomized search. So basically, the idea is to propose an algorithm which is repeated for a limited amount of time. The algorithm finds several solutions and keep the best. And the core of the algorithm is the one we call compiled circuit, which is a random algorithm, which each time you run this algorithm, you get a different compilation. So at the end, we return the best solution. The application we have proposed is a problem which can be defined according to this way. So we have a set of ground communication from a set of satellite. There is a set of ground station which can receive the communication. They have a unary capacity, so one communication at a time. Each satellite can use only a subset of the available ground station. And we just match, the problem is to match communication to ground station in order to remove all the conflicts, or at least maximize the number of non-conflicting communication. And so we have tested our algorithm respect to a suite of compiling algorithms available in QSkit. So here the name, basic swap, stochastic swap, sample swap, look-ahead swap. And here you see on the right the performance of algorithm on a benchmark we have proposed respect to 10 seconds run for each algorithm, and we measure the performance with the depth. It means the depth is the overall duration, in some sense, is proportional to the overall duration of the circuit, the overall length of the circuit. This is a very important measure because it affects the coherence of the circuit. And as you can, our algorithm is called GRS, is on this subset, on our benchmark, the performance are quite good or comparable with the one proposed, the other one proposed in QScript. But we will see this, the details of this presentation, of these results in the second part of the presentation. Now, so this is my, I finished the executive summary. Thanks a lot. So.
Okay, thanks a lot. So this was
okay.
The executive summary, right? And maybe we can stop here for a second and see if anyone has questions before we go